Gallo-Torneria performs precision machining using CNC lathes and milling machines. The process begins with loading raw metal bars into automatic CNC lathes, which carry out high-precision turning operations. Parts are then transferred to CNC milling machines for further shaping, drilling, or slotting as required. Throughout the process, multi-axis machines ensure complex geometries and tight tolerances. After machining, each part undergoes dimensional inspection using advanced measuring equipment to ensure compliance with quality standards. Skilled technicians monitor every stage to guarantee accuracy and consistency. The combination of automated systems and manual expertise allows the company to produce high-precision mechanical components for various industrial applications. The process begins with the preparation of the original 6-inch steel wheel. The technician mounts the wheel onto a stable surface to ensure precise control during cutting. Using a rotary cutting tool, the wheel is cut along the intersection of the rim. The cutting location is selected to maintain structural integrity while allowing for an accurate insertion of new material. The cut is made completely around the wheel's circumference, dividing it into two separate parts. Once the wheel is split, the technician proceeds to clean and grind the cut surfaces. An angle grinder is used to smooth the edges and remove any burrs, rust, paint, or debris that could interfere with welding. Both the inner and outer edges of the cut wheel are thoroughly prepared. Additionally, the technician grinds the outer surface of the wheel to ensure a clean bonding area for the added section. Next, a new steel band with a predetermined width enough to increase the overall wheel width to 9.5 inches is prepared. This steel insert is formed into a perfect ring matching the diameter of the wheel. It is then carefully positioned between the two cut halves of the original wheel. Alignment is critical at this stage to ensure the wheel remains perfectly round and balanced after welding. The technician then begins the welding phase. Tack welds are applied at multiple points around the wheel to hold the new section in place. Once secure, a full weld bead is applied along both joints where the insert connects to the original wheel parts. This continuous welding ensures a strong, durable, and airtight bond. The welding is performed slowly and uniformly, both on the outside and inside surfaces. After welding, the joints are once again ground down to remove excess weld material and to achieve a smooth, flush surface. The entire wheel is then checked for any warping or deformation caused by heat during welding. The technician mounts the wheel on a spindle or balancing stand to inspect its roundness and ensure it spins evenly. The final product is a widened steel wheel, expanded from its original 6-inch width to 9.5 inches. This process is commonly used in custom automotive applications to accommodate wider tires, improve vehicle aesthetics, or achieve specific performance characteristics. The gear manufacturing process begins by mounting the blank onto the MAAG SH150 gear shaper. A single-point cutting tool is aligned precisely with the workpiece. As the machine operates, the tool reciprocates vertically while the gear blank rotates in synchronization, gradually forming each tooth. The process is slow but highly precise, ideal for large module gears. In this case, a 24-module gear with 22 teeth is cut. Continuous indexing ensures all teeth are uniformly shaped. Once all teeth are formed, the gear is removed, completing the shaping process. The turret bearing was cut with a heat cutter, due to excessive clearance and lack of warranty from the supplier. The bearing, made of carbon steel with heat-treated rollers and an inconel coating, was too large for conventional cutting. A heat cutter, consisting of iron rods inside a conduit with an oxygen flow, was ignited with an oxyacetylene torch. After ignition, the cutter burned at a temperature of approximately 4,000 degrees Celsius, melting the hard materials of the bearing. When the cutter was burned, the operator stopped the oxygen flow, removed the remaining part, and installed a new cutter to continue cutting until the job was done. The SPM automation machine performs the controlled fracture of connecting rods with high precision. First, the rod is clamped securely in position. Then, a predefined notch guides the fracture point. A hydraulic or mechanical force is applied to split the rod cleanly along the notch, creating a perfect mating surface. Sensors monitor the process, ensuring consistency and quality. Finally, the fractured parts are separated and moved automatically for further processing, optimizing productivity and eliminating the need for manual handling. GmbH, founded in 1908, is one of Europe's leading steel casting manufacturers. Upholding its long-standing values of quality and innovation, the company produces top-tier castings used in valves, pumps, energy systems, and various machinery. Depending on application, materials range from low to highly alloyed steels and nickel-based alloys. To meet the highest safety standards, the production process includes strict quality controls and full documentation. The company is fully equipped to perform all standard surface crack, volumetric, and destructive tests in-house. Advanced technologies, such as computer-aided solidification simulations and CNC machining, ensure precision and efficiency. Additionally, it offers tailored solutions for welded structures. With over 300 skilled employees and a strong export rate exceeding 50%, GmbH delivers cast products that meet global demands with excellence. The process begins with marine surveys to map the ocean floor. Then, the submarine cable is manufactured in long sections and coiled onto massive spools. These spools are loaded onto specialized cable-laying ships. At sea, the cable is gradually laid on the ocean bed. In shallow areas, remotely operated plows bury the cable beneath the seabed for protection. Finally, the cable is brought ashore and connected to landing stations, completing the link between countries like the US and Japan. The iron casting process at Saudi Cyprus Foundries Limited begins with re-engineering and pattern making in the pattern shop. Patterns are prepared based on specifications, then used in the molding section to form sand molds. Meanwhile, raw materials are stored and managed in the store. In the melting and pouring stage, Metal is melted in furnaces and carefully poured into the prepared molds. Once cooled, the shakeout process removes the castings from the sand molds. The raw castings then proceed to the finishing area where they are cleaned, ground, and refined to remove any imperfections. Finally, quality testing is conducted to ensure each casting meets the required standards before shipment. This systematic process ensures high-quality iron castings. The forging process at Lucchini RS begins with ingots, followed by electroslag remelting to enhance material quality. The remelted ingots are then heated and forged using a powerful press. Subsequent heat treatments improve mechanical properties. Finally, the parts undergo rough and finish machining to achieve the required dimensions and surface finish. The steel production process at Usiminas begins with the arrival of raw materials, mainly iron ore and coal, through maritime and rail transport to the plants. In the coke-making area, mineral coal is heated in ovens at temperatures exceeding 1,000 degrees Celsius for 16 to 18 hours, transforming it into metallurgical coke and producing coke oven gas. After specific treatments, this gas is either reused as fuel in the plant or sold for use in the plastics, fertilizer, and pharmaceutical industries. Next, in the sintering area, fine iron ore is mixed with fluxes and heated to form sinter, a porous material that is also fed into the blast furnace. In the blast furnace, iron ore, sinter, pellets, and coke are layered from the top, while hot air at 1,200 degrees Celsius, pulverized coal, and natural gas are injected from the bottom. As the materials descend, chemical reactions occur, resulting in the formation of molten pig iron, which accumulates at the bottom of the furnace. Once the furnace tap hole is opened, the molten iron flows through the runner into torpedo cars and is transported to the steel plant. At the steel plant, the pig iron undergoes desulfurization to reduce sulfur content. It is then transferred into a converter along with steel scrap. A lance blows pure oxygen into the molten metal to reduce carbon and phosphorus, transforming pig iron into steel. Alloying elements are added during secondary metallurgy in a ladle to achieve the required physical and chemical properties. Temperature and chemical composition are further adjusted during this stage. The refined liquid steel is cast in a continuous casting machine to form solid slabs. These slabs are cut to length, inspected, and either sent to rolling mills or sold directly to customers. In hot rolling, slabs are reheated and reduced in thickness through rolling to produce hot-rolled plates and coils. These products are used in heavy machinery, tanks, industrial equipment, and construction. Some hot-rolled coils are further processed through pickling, cold rolling, annealing, and skin passing to produce cold-rolled coils and sheets with enhanced surface quality and mechanical properties. Cold-rolled products are widely used in automotive, appliances, furniture, and metal doors and windows. For added corrosion protection, cold-rolled coils may undergo electrogalvanizing or hot-dip galvanizing. The final products are inspected, identified, packaged, and distributed through Usiminas' integrated logistics and service centers to meet customer requirements with excellence and efficiency. The Coro Mill 390 demonstrates a highly efficient milling process in various operations. The demonstration begins with shoulder milling, where the tool performs smooth cuts along the workpiece edges, delivering high-dimensional accuracy and surface quality. The tool then executes ramp milling, descending into the material at a controlled angle, showcasing its optimized cutting geometry that minimizes cutting forces and ensures vibration-free machining. Next, the tool performs helical interpolation, where it follows a spiral path to mill deep cavities without pre-drilling, emphasizing the cutter's ability to maintain stability even with long overhangs. This is enabled by the integrated damped tool holder, which significantly reduces vibrations during extended reach operations. Following this, the Coro Mill 390 engages in pocket milling, clearing large areas efficiently while maintaining sharp corners, demonstrating excellent chip evacuation. The tool's light cutting action is evident as it seamlessly transitions between cuts, even in harder materials like steel or stainless steel. The process concludes with slot milling and face milling, where the tool showcases its multi-edge engagement, providing a uniform surface finish and consistent depth. Throughout the video, the tool operates under high-performance parameters with various mounting options, illustrating its adaptability in complex machining setups. The result is a reliable, quiet, and precise machining process across a wide range of materials and operations. Located in York, Pennsylvania, Voith Hydro is one of the world's largest hydropower manufacturing facilities, and the only one in North America with a hydraulic test lab. With over 500 experts, it designs, builds, and refurbishes clean, efficient hydroelectric equipment. The production process of GSP Automotive steering and suspension components begins with reverse engineering based on detailed specifications. In-house mold design and manufacturing ensure precise shaping. High-quality raw materials, produced by a furnace operating at 730 degrees Celsius to 750 degrees Celsius, are controlled according to ISO 209-2007 standards. These materials undergo heavy-duty extrusion using equipment with a maximum pressure of 1,350 tons. Automatic rolling, forging, and pressing are followed by superior forging using machines up to 5,000 power tons. Crack detection is performed via an automatic fluorescence inspection system. T6 heat treatment is applied to enhance mechanical properties. Components are then processed with 4D CNC machining and 360-degree surface shot blasting. Oxidation is automatically applied, maintaining corrosion resistance under the zero-defect policy. High-precision CNC machining and mirror finishing follow. Multi-stage machining centers complete the shaping process. Assembly involves ball seat installation, spin riveting, crease filling, clamp assembly, and press riveting. Each unit undergoes an automatic swing torque test post-assembly. "12 robotic welding lines ensure consistency. Comprehensive quality control includes roundness, hardness, tensile, and pull-out tests, along with rubber tensile and durability tests for ball joints. Environmental testing ranges from -40 degrees Celsius to +120 degrees Celsius with up to 1 million cycles. Finally, salt spray testing and final inspections are conducted before parts are stored or dispatched from the CSP Logistics Center. The Turbo 10 shell end mill with a 32 mm diameter is used on a Mori-Seiki machine for various metal milling operations using SS2244 material. Equipped with ME07 F40M inserts, the cutter performs plunge milling with a cutting speed of 200 meters per minute, a feed per tooth of 0.17 millimeters, and an axial depth of 4 millimeters. During slot milling, the same tool configuration is used with a depth of 7 millimeters, maintaining consistent speed and feed settings. In the ramping pocketing process, the tool mills into the material at a 1.7 degrees angle with a depth of 1.7 millimeters, using the same feed and cutting speed. The Turbo 10 also performs shoulder and slot milling, cutting at depths of 7 millimeters and 8.5 millimeters respectively. Throughout all operations, the cutter operates at 1,360 millimeters per minute feed rate, offering excellent chip evacuation and surface finish. Thanks to the rigid arbor-type connection and multi-tooth configuration, the Turbo 10 ensures high stability and productivity during metal removal. Its versatile performance across plunge, slot, ramping, and shoulder milling showcases the cutter's efficiency on small to medium milling machines. Brightpan manufactures most of the small parts used to assemble their buildings. Each part and subcomponent has its own production order and blueprint, which are created by the engineering department to match customer requirements. Quality checks begin at the welding stage, where the welder ensures that the parts meet blueprint specifications. Welding is done either manually using fixtures or with the assistance of welding robots. Various in-house tools and machines are employed to make small parts. For instance, webbing is bent using a CNC-controlled tube bending machine programmed via VenPro software. This ensures that the parts will fit when reaching the weld station. Tubes up to 1.5 inches in diameter and 170 inches long can be bent in just 90 seconds. Afterwards, the tube ends are clipped using an iron worker to prepare them for welding. Brightspan's cold saw can process pipe up to 4.5 inches in diameter and 48 feet in length. For leg manufacturing, both round and square tubes are drilled using templates that guarantee repeatability. Operators self-check their work before it is passed to the quality technician for inspection and then sent to the final weld station. The company's Epic and Genesis building series are fabricated in two large welding cells. Welders work in teams to tack and weld large trusses. Due to the subcomponent size, 3-ton and 5-ton cranes are used to move and position them. Once welding is complete, each part is inspected to ensure it matches all specifications. A key piece of equipment at Brightspan is the Davi roller, which rolls pipe up to 4.5 inches in diameter and 0.25 inches thick. It is numerically controlled and programmed to produce precise radii. After rolling, parts are verified using the quality control table, with templates or gauges made by qualified welders. All parts, whether made in-house or supplied, undergo a receiving inspection before welding. This inspection checks blueprint dimensions and quantities. Truss assemblies are validated for dimension accuracy, and depending on the production run, up to 4 assemblies may be checked to confirm structural integrity. Final products undergo full inspection before shipping for galvanizing or customer delivery. Quality technicians and supervisors are certified. Subcomponents are verified to match production orders and blueprints before welding begins. Each shift also inspects the previous shift's work. Weldments must be performed in a flat position. In the small welding cells, a 1-ton crane assists in handling. Visual management boards at each station ensure that welders have access to production orders, blueprints, weld procedures, lockout instructions, and production targets. Every part is identified with a part number to simplify installation. Welding jigs are rotated manually or with mechanical rotators. After welding, parts are cleaned, inspected, bundled, and moved to the quality assurance area for final inspection and shipping. Brightpan maintains an inventory worth over $4 million. Welders assemble parts and fixtures, after which a robot tacks and completes the final welds. Welds are inspected to ensure compliance with specifications. The large robot operates in both the large building cells and a smaller component station. Subcomponents are inspected before they are fitted into fixtures for tack welding. After tacking, large cranes assist in final welding. Welds in critical dimensions are inspected again before the components are staged for final review by quality technicians. The bandsaw is used to cut subcomponents to length and to process hollow structural sections, which are hot-dip galvanized before use. HSS are used primarily in end walls. Templates are applied to ensure field alignment. Although swaging is mostly performed by suppliers, Brightpan can swage in-house to reduce material diameter, allowing pieces to connect into continuous pipes. The Whitney plasma punch table cuts and punches holes in steel sheets up to 1/2 inch thick and 5 feet x 10 feet in size. Operators confirm die setups, then verify the first part before continuing. All incoming parts are reviewed by quality technicians, then released for welding. Purlins are made by flattening both pipe ends with hydraulic presses and punching holes using an iron worker. They support truss sections and can be made from pre-galvanized or hot-dip galvanized materials in different diameters and lengths. The plasma cutter, a CNC cutting machine, processes pipe into programmed profiles. It handles subcomponents for base rail systems and stick webbing for larger building series. A parts cleaner removes scale, slag, and burrs from small parts in about 5 minutes before final inspection and release to manufacturing. Trusses are shipped to a galvanizing facility after fabrication and welding. They are cleaned to remove contaminants and then dipped into molten zinc for full galvanization. Unlike pre-galvanized trusses that risk internal rusting, Brightpan's post-welding galvanizing ensures long-lasting protection. After returning from galvanizing, trusses are prepared for assembly. Posts are used for separation, and each hole and mating surface is checked. Rough or contaminated areas on outer cords are sanded smooth. Trusses are then bundled with bolts and wood spacers to avoid damage. Finally, once fully cleaned and inspected, a sticker certifying 100% verification is applied. This final approval comes from the finishing supervisor and the distribution department, ensuring each shipment is ready for timely delivery.